The next data structure we're going to learn about is a binary search tree. Binary search trees make some operations pretty fast and will be the basis of advanced data structures that you'll see later on in CSC148 and maybe other courses. In this video, we're going to take trees and use them to implement the multi-set ADT, also called the collection ADT, which supports the following behaviors. First, checking to see if the collection is empty. Second, checking to see if an item is in the collection. Third, adding stuff to the collection. And fourth, removing stuff from the collection. Now, this is a little bit more flexible than stuff like stack and queue because you can actually pick what you want to add or remove and where they're going to go. Because removing an item requires you to search the collection to see if the item is actually there, this abstract data type is also going to support contains, basically searching the collection by a value rather than by the position. And it's this behavior that we're going to start by focusing on. For a list, the obvious algorithm to figure out if something is in the list is to go through each one by one from start to finish and stop when you find it. When something's not there, you have to check everything, which means that this is a linear time operation. The time it takes to complete your unsuccessful search is directly proportional to the length of the list. With tree contains, we have kind of the same behavior, right? If the item is not in the tree, you have to check everything in the tree because it could be anywhere. So switching from a list to a tree doesn't really make any difference here. However, one of the benefits and things that we note in computer science is that adding additional structures to data can enable new algorithms that are more efficient. This is called augmentation, making a change purposefully so that we can improve some other behavior that we're interested in focusing on. You've probably seen this already in some of the other labs that we've done, but we're going to look specifically at some complex structures imposed on data here. In the case of a Python list, for example, if the list is sorted, there is an algorithm we can use to search more quickly called binary search. It greatly improves things, and you can probably go back and check out CSC148 to remind yourself why binary search works the way it does and why it's faster. But because this is still built on an array-based list, we have sort of the same drawbacks for insertion and deletion from before. So the question is, can we get efficient search, insertion, and deletion all at the same time? And the answer is yes. Now, to do so, we're going to combine the branching structure of trees, parents and their children, with the idea of binary search to develop this idea of a sorted tree, and we're going to call this a binary search tree. So there's a couple terms that we want to focus on here. First off, binary, meaning two, means that a binary tree is a tree where each item has at most two subtrees. You could have 0 if you're just a root with nothing. You could have 1, you could have 2, but you can't have any nodes that have 3 or more children. So in a binary search tree, we first off have the rule that you can't have any more than 2 subtrees. And secondly, we have what's called the binary search tree property. And this property is every item in your tree needs to have a value greater or equal than everything in the left subtree and less than or equal to everything in the right subtree. So a binary tree is a binary search tree only if every item in the tree has the binary search tree property. So the every is important. So it's very necessary that you actually have, and if you're thinking about this conceptually, your root is your middle point. Everything on the left side, is it this side? I can't tell how the camera is going to handle this. Everything on the left side, whichever side you're looking at, is smaller than that root. Everything on the right side is bigger than that root. And that property holds true for the subtrees that are there. So if we go right from our starting point and now we're looking at a new subtree, the rules still apply there. What this means is that, let's suppose you have your root is, 10. In your right subtree, maybe the root of that is 15. This is okay now. 15 is bigger than 10. If you have something that's to the left of that 15, that subtree that's there, it must still be greater than 10 because it can't be, in order to be in that right subtree from the 10, it must be bigger than 10. Otherwise, you have actually broken the binary search tree property. Now, binary search trees are basically a way that we can represent sorted data. In other words, even if the data doesn't show up in sorted order, the binary search tree will keep track of it in that way. This means that they're very efficient in terms of searching. And unlike in a Python sorted list, it can be very efficient at insertion and deletion while still staying sorted.